Photoconductivity and photovoltaics. Photoconductivity and photovoltaics. Photoconductivity. In an insulating crystals. Variation of photoconductivity. With illumination. Effects of traps. Applications of photoconductivity. Photoconductive cells. And photovoltaic cell. Photodiode. Photovoltaics. Solar cells. And their characteristics. Photoconductivity. In an insulating crystals. The phenomenon of an increase in the electrical conductivity of an insulating crystal. When the light radiation falls on the crystal is called photoconductivity. Note: we are talking about an insulating crystal, which normally does not have free electrons to carry current, and the electric conductivity is very poor. Some of the basic experimental work was done by Giddens and Pohl, and they concluded as number 1. The light absorption and the excitation of photoconductivity by the light had a similar dependence on the wavelength of light for a given material. The effect of photons absorption is to increase the number of mobile charge carrier in a crystal when the energy of the photon, HNU, is more than the energy gap, e.g., it generates free electron hole pair, which enhances the electrical conductivity. Note: energy gap, e.g., is the intrinsic property of the material, so is the response to the photon with typical energy, or wavelength or frequency Nu, for the photoconductivity. Note the energy gap between conduction band and the basic valence band. Note: there is no forbidden energy gap in metals and good electric conductors. Some gap in semiconductors and high to very high in insulators. The crystal is the purest form of a material. Even in crystal there are some defects and impurities which affect the electrical conductivity. It was confirmed by deliberately introducing impurity. It was found. Number 2. The presence of impurities extended the region of photosensitivity to longer wavelengths, infrared or lower frequency or energy. Defect in crystals introduces discrete energy level in the forbidden energy gap, which are often called traps. Number 3. Some impurities could reduce the photosensitivity of the material. Let's discuss a simple model of photoconductor. In a simple model of photoconductor, the electron-hole pairs are produced uniformly in the crystal by an external light. Recombination of electrons and holes also occurs. The increase in electrons will contribute to the photocurrent, assuming the electron leaving one electrode are replaced by electron flowing in from the opposite electrodes. We work on the mobility of the electrons. Based on this model, the rate of change of the electron concentration N depends directly to the number of photons absorbed. Say L is given by dN or dt equals L minus ANP. The term ANP gives the recombination rate. N and P represent number of electrons and hole, respectively, and A is a proportionality constant. Assuming number of electrons N equals P, number of holes, the rate of change of hole concentration P is given by dP or dt equals L minus ANP equals L minus AN square. In steady state, there is no rate of change of electron or hole. In steady state, there is no rate of change of electron or hole. So dN or dt equals 0, or dN or dt equals L minus AN square equals 0, which gives L minus AN square equals 0. Therefore in the steady state, the electron concentration is N0. L equals AN0 square. Or N0 equals square root L divided by A. And photoconductivity sigma is as by definition sigma equals N0 E mu, where mu is the electron mobility and E is electron charge, or sigma equals E mu square root L divided by A. From this simple model of photoconductor, which predicts a relation between photocurrent and light intensity, that is at a given voltage, the photocurrent will vary with light intensity as square root L. However, the observed exponent is not exactly half, but is usually between half and 1. For example, in case of cadmium sulfides, CDS crystal, the exponent varies between 0.92 at low levels and 0.58 at high level of illumination. After the steady state, if the light is switched off, or L equals 0, the decay of photoelectrons will start, and will be given by dN or dt equals minus AN square, from dN or dt equals L minus AN square, or dN divided by N square, equals minus A, dt. Solving the differential equation by integration, minus 1 or N equals minus AT plus C. To calculate constant C at switch off, the time t equals 0, when the light L equals 0 number of electrons. Is n equals n0 at this condition? C equals -1 divided by n0. Or we have 1 divided by n equals AT plus 1 divided by n0. From 1 divided by n equals AT plus 1 divided by n0, we calculate the response time T0, which is the time taken crystal to drop the carrier concentration to 1/2 of its value at T equals 0, or 1/2 n0. We rewrite 1 divided by n equals AT plus 1 divided by n0. Or 1 divided by n0 by 2 equals AT0 plus 1 divided by n0. Or AT0 equals 2 divided by n0 minus 1 divided by n0. Or T0 equals 1 divided by n0 equals 1 divided by square root LA. Or T0 equals n0 or L, by replacing A equals L divided by n0 square. Combining with sigma equals E mu times square root L divided by A, we get T0 equals sigma divided by L E mu. Thus, it predicts that the response time T0 is directly proportional to the photoconductivity of the crystal at a given value of illumination level L. Sensitivity, or gain factor. The sensitivity of a photoconductor, or gain factor G, is defined as the ratio of the number of carriers crossing the specimen to the number of photons absorbed in. If D is the thickness of the specimen, then the voltage V produces the particle current I, or number of carrier crossing, is given by Jn equals I divided by E equals N0 mu dot V divided by D equals mu V square root L by A divided by D, from N0 equals square root L divided by A. G equals particle flux divided by LD equals Jn divided by LD, or G equals Jn divided by LD equals mu V divided by D square root LA. Td is the transit time, the time taken by a carrier to move from one electrode to the other electrode at a distance of d. Td equals d divided by mu dot v divided by d, or Td equals d square divided by mu dot v. Also, Te, the time of the electron remain free before they are recombined, is given by Te equals 1 divided by square root L A. Thus the gain G can be expressed as G equals Te divided by Td. That is, the gain is equal to the ratio of the carrier lifetime to the transit time of a carrier between electrodes. Please note, to increase the gain G, increase Te and reduce Td. Traps. A trap is an impurity atom or other imperfection in the crystal capable of capturing an electron or hole. The captured carrier may be re-emitted at a subsequent time and may move to another trap. There are two types of traps. First type, which help recombination of electron and holes. This type of traps are known as recombination centers. Second type of traps does not contribute directly to recombination, but affects the freedom of motion of charge carriers. Here we show animated action in crystals. When photons strike the crystal, if the energy of the photon HNU is more than T, forbidden gap energy, it will lift electron from valence band to conduction band. But due to presence of traps, electron may not go straight to conduction band, but pause in a trap and later move to conduction band. Traps also help electrons to move, even if the photon energy is less than forbidden gap. Recombination center increase the current flow. Consider a crystal with capital N is numbers of electron trap levels per unit volume. Suppose that the temperature is sufficiently low in relation to the relevant ionization energies so that the concentration of thermal carriers may be neglected. Assume that the recombination coefficient A is same for electron and hole recombination as for electron and trap capture. Then we modify dN or dt equals L minus AN times N plus N, where N is the concentration in the conduction band. In the steady state, dN or dt equals 0 and N equals N0. We have L equals AN0, N0 plus N, or N0 times N0 plus N equals L divided by A. Here, we discuss two limiting cases with respect to N. Number 1. It is difficult to grow crystals with trap concentration capital N much less than 10 to the power of 14 per centimeter cube. At low current levels, the carrier concentration N0 is far less than the capital N. We have N0 equals L divided by AN, neglecting N0 square in N0 times N0 plus N equals L divided by A. In this case, the photocurrent is now directly proportional to the illumination level L. Effects of traps. Number 2. Second case we consider when photoillumination is at high levels, so N0 is far greater than capital N. Then, neglecting N in N0, N0 plus N equals L divided by A. Or N0 equals L divided by A to the power of 1/2. This is same as found earlier in a simple model of photoconductors, that when we did not consider traps, or you can say, in the absence of traps. Note in the graph, the experimental results confirm this change in the response with illumination level from low to high. We discuss now the steady-state case. What will happen when illumination is off, or L equals 0 at T equals 0? The decay of the carriers, photoelectrons, on switching off the light, L equals 0, is given by dN dt equals minus AN times N plus N, or dN divided by N plus N equals minus A dt. Solving this differential equation by integration, log n minus log n plus n equals minus ant plus c. To get the constant of integration c, we apply the condition. At the time when illumination goes off or t equals 0, n equals n0, then c equals log n0 divided by n0 plus n. Finally, ant equals log n plus n divided by n minus log n0 plus n divided by n0. Ant equals log n plus n divided by n minus log n0 plus n divided by n0. When the number of trap are high, capital N is far greater than n. The solution reduced to n equals n0 exponential of minus ant, and response time is t0 equals 1 divided by na. Comparing this result with earlier result of simple model of photoconductor. In the absence of traps, the presence of traps reduces the conductivity and also reduces the response time. Photoconductive cell. Photoconductive cell principle. Photoconductive cells are based on the principle that the electrical resistance of semiconductor materials decreases when they are exposed to radiations. For example, a cell made of a thin layer of semiconductor material such as lead sulfide, lead selenium, cadmium sulfide, CDS, etc. The amount of this decrease depends on the intensity and frequency of the incident light. Therefore, if such a substance is inserted in the circuit and light is allowed to fall on it, its electrical resistance will change. If a photon striking the surface of such photosensitive material has energy E equals hnu greater than the energy gap between the valence and conduction bands of the material, this sufficient energy will be imparted to an electron to raise it to the conduction level. Consequently, a hole is left in the valence band. This electron-hole pair is free to serve as current carriers, and hence, the conductivity of the material increases or the electrical resistance is reduced. Constitution and working of the photoconductivity cell. The materials generally used in photoconductive cells are cadmium sulfide, CDS, or lead sulfide, PBS. Commonly used photoconductive cell is CDS cell. In this cell, a thin film of CDS is deposited on one side of an iron plate and placed below a transparent foil of metal. When light radiations fall on transparent metal foil, the electrical resistance of CDS layer is reduced. As a result, a current starts flowing in the circuit connected between the iron plate and the transparent metal film. One external battery is included in the circuit to generate a direction and Provide a path for a current to flow. Here is the diagram of a photoconductive cell. Characteristics. The characteristics of a CDS cell, showing the relationship between illumination and resistances. In the figure, it may be seen that when there is no illumination, in absolute darkness, the cell has a resistance in the range of 100K, which is called dark resistance. When illuminated with strong light, the cell resistance falls to only a few hundred ohms. Thus the ratio of dark to light resistance of the cell is about 1000 to 1. Note here, the response to light is very similar to what we see through our eyes. Spectral response. The response is sensitive to visible light. It is very closely matches the response of human eye. Applications. There are hundreds of applications of a photoconductive cell, but for academic purpose, we select few here. 1. To measure the intensity of illumination, to make it as to work as light meters. With the help of light meters, the lights are adjusted uniformly in indoor stadium, or in the field of football or cricket in the night. Two. By flashing of light remotely on the photoconductor, we can make it to work as on-off switch. 3. By setting at certain light level, the photoconductor are used in automated street lighting to counter the adverse effect of weather. 4. In camera exposure settings. 5. In counting applications. 6. In burglar alarm. 7. In aircraft and missile tracking system. Some advantages. The principal merits of CDS photoconductive cells are: 1. High sensitivity. 2. Low cost. 3. Long life. 4. High dissipation capability. 5. High voltage capability, 100 to 300 volts. 6. High dark to light resistance ratio, 1000 to 1. Drawbacks and shortcomings. 1. The current changes with change in light intensity, with a time lag. 2. Slow response time compared to other types of light detectors. 3. A relatively narrow spectral response. 4. Temperature sensitivity. 5. Noise. Photodiodes. Photodiodes. A photodiode is a semiconductor diode sensitive to photon radiation, such as visible light, infrared or ultraviolet radiation, and even to X-rays and gamma rays. It produces an electrical current when it absorbs photons. A photodiode is a reverse-biased p-n junction diode, which is designed to respond to photon absorption. Typical VI characteristic of a diode. In forward bias, the diode carry a large amount of the current, while in reverse bias, there is hardly any current. The effect of photon on current is only noticeable when diode is put in reverse bias. And it is directly in proportion to the illumination. Principle of a photodiode. A reverse-biased p-n junction diode has a small reverse saturation current, which is mainly due to the flow of the minority carriers. If light is allowed to fall on such a reverse-biased p-n junction diode, additional electron-hole pairs are generated in both p and n regions. It produces a very large change in minority carrier concentration, and hence increases the reverse current through the diode. The current through the diode varies almost linearly with the light flux. Working and characteristics. When photodiode is kept under dark condition and a sufficient reverse voltage is applied, then an almost constant current, independent of magnitude of reverse bias, is obtained. This current corresponds to the reverse saturation current due to thermally generated minority carriers, and is called dark current because it flows when no light is incident. It is proportional to the concentrations of minority carriers, holes in N and electrons in P region. It produces a very large change in minority carrier concentration, and hence increases the reverse current through the diode. The current through the diode varies almost linearly with the light flux. When light is incident on the photodiode, additional electron-hole pair are formed. Note the percentage increase in majority carrier is very small as compared to minority carrier. We focus only on the increase in minority carrier due to light, which contribute to additional current. Thus, under the large reverse bias condition, the total reverse current is the sum of I equals ID plus IS, where IS is the short circuit current and is proportional to light intensity. ID is reverse saturation current or dark current. Uses. Photodiode is very fast and can turn its current on and off in nanoseconds. Hence it is used where light is required to be switched off and on at a very fast rate. A photodiode is used in light detection, in light-operated switches, reading of computer-punched cards, and types, etc. Photodiode find applications in optical communication system. They find many uses in instrumentation, control, automation, and communication. Photovoltaic cell. So far, we focused on the photoconductivity and photodiodes. In photoconductive mode, the diode is reverse biased. That is, with the cathode driven positive with respect to the anode. Now, we explore diodes in photovoltaic mode. Becquerel in 1839 discovered that when a pair of electrodes is immersed in an electrolyte, and light is allowed to incident on one of them, a potential difference is created between the electrodes. This phenomenon is called photovoltaic effect. Devices based on this effect are known as photovoltaic cells. Thus, photovoltaic cells are the devices in which light energy is used to create a potential difference. The potential difference, so developed photovoltaic cells, is directly proportional to the frequency and intensity of the incident light. In photovoltaic mode, the diode is zero biased or in open circuit. If the circuit is opened or has a high load impedance, which restricts the photocurrent out of the device, so a voltage builds up in the direction that forward biases the diode, that is, anode positive with respect to cathode. Construction and working. A basic photovoltaic cell consists of a piece of semiconducting material bonded to a metal plate. Materials like selenium and silicon are mostly used for preparing photovoltaic cells. In constructing a photovoltaic cell, a thin metallic film of silver or gold is deposited on a semiconducting layer, like cuprous oxide, Cu2O, or iron selenide. The whole arrangement is then attached to a copper base plate. You saw that the construction and now working of the cell, when external light is made to fall on transparent conducting metallic film, it penetrates to the semiconductor, and photoelectric emission occurs. In semiconducting material, valence electrons and holes are liberated from its crystal structure. The emitted photoelectrons move towards the metallic film, and the metallic film becomes negatively charged, and the copper base plate positively charged. Hence, a potential difference is developed between the two, and a current flows in the external circuit. The strength of the current is proportional to the intensity of light, and flows without any bias. Solar cell. Solar cell. Solar cells, also known as photovoltaic (PV) cells, convert sunlight directly into electricity through the photovoltaic effect, using semiconductor materials like silicon to generate electron-hole pairs when exposed to light, which then flow as an electric current. A solar cell is basically a p-n junction diode, which converts solar energy into electrical energy. It is simply a photodiode operated at zero bias voltage. When the circuit is shorted, or the impedance is low, a forward current will consume all or some of the photocurrent. This mode exploits the photovoltaic effect. This is the basic principle of a solar cell. A traditional solar cell is just a large area photodiode. For optimum power output, the photovoltaic cell will be operated at a voltage that causes only a small forward current compared to the photocurrent. Construction. A solar cell consists of a p-n junction diode, generally made of germanium or silicon. It may also be made with other semiconducting materials like gallium arsenide, indium arsenide, and cadmium arsenide. The PN diodes so formed is packed in a can with glass window on top so that light may fall upon P and N-type materials. The thickness of the P region, that electrons generated in this region can diffuse to the junction before recombination takes place. Thickness of N region is also kept small to allow holes generated near the surface to diffuse to the junction before they recombine. A heavy doping of P and N region is recommended to obtain a large photovoltage. A nickel plate ring is provided around the P layer, which acts as the positive output terminal. A metal contact at the bottom serves as the negative output terminal. Watch the diagram of a solar cell showing different parts. When light is allowed to fall on PN junction diode, photons collide with valence electrons and impart them sufficient energy, enabling them to leave their parent atoms. Thus electron-hole pairs are generated in both the P and N sides of the junction. These electrons and holes reach the depletion region. By diffusion, they are separated by the strong barrier field existing there. However, the minority carriers, electrons in the P side, slide down the barrier potential to reach the N side, and the holes in the N side move to P side. Another diagram to show you inside the depletion layer. Their flow constitutes the minority current, which is directly proportional to the illumination and also depends on the surface area being exposed to light. The accumulation of electrons and holes on the two sides of the junction gives rise to an open circuit voltage. The open circuit voltage produced for a silicon solar cell is typically 0.6 volt, and the short circuit current is about 40 milliamperes per centimeter squares in bright noonday sunlight. Power conversion efficiency of about 15% is obtained. Many such cells are interconnected to provide large quantities of electrical power. In a solar panels providing 5 watt at 12 volts. Voltage versus current characteristics. Note on VI graph. When circuit is closed with zero impedance, we get maximum current, but voltage is zero between anode and cathode. And when impedance is very high, the current is very low, but voltage accumulated at the anode is maximum. As the power equals V times I, we get the maximum power out when both VI are relatively high, which is at the turning point or knee point of the curve at all the illumination level. Characteristics. Voltage versus current characteristics of a solar cell, corresponding to different levels of illumination, are just shown in last figure. It may be seen that 100 milliwatts per square centimeter illumination, the open circuit voltage, is about 0.57 volt, while the short circuit current is 50 milliamperes. Maximum power output is obtained when the cell is operated at the knee of the curve. Uses. Multiple solar cells in combinations of parallel and series orientations form an integrated group, all oriented in one plane, constitute a solar panel, and are used in satellites and space station, electric vehicles, terrestrial electric power generation, home power, calculators, remotes, watches, and other gadgets. Now leading sources of unconventional energy all over the world, which is environment friendly. Thank you for watching this video. Please continue to watch our other videos. Thanks.